Okay, perfect. So please all take a seat if you still find free seats. If not, you have to stand. Yes, perfect. So welcome to our last colloquium for this summer. We have Adam Kaufman from Gila here today. He actually recently won the Bessel Award from the Humboldt Foundation. So he will come here more often, we hope. Well, at least it's planned. So this summer he was here for about 6 weeks and he will come back next summer. And Adam is an expert on developing platforms for quantum simulation and quantum computation with neutral atoms, combining lattice potentials and local control using optical tweezers. And as you can see from the title, also combined with optical clock techniques and actually using these control techniques in order to engineer interesting entangled state that could be useful for metrology. To give you a little bit of background information, Adam did his PhD at Gila and then moved to Harvard to do his postdoc in a group of Markus Greiner, where he was working on quantum simulation with neutral atoms using quantum gas microscopy. And since 2017, he is at Gila, establishing his own group, which by now is already quite big. And we will hear mostly, I think, about the strontium results. He has received a number of other awards. I just mentioned two from last year, I think, which is the Rabi Prize and the New Horizons in Physics Prize. So please enjoy the talk.
All right, thanks so much for the introduction, also the invitation to be here. It's been a great visit so far, and I definitely will be coming back. So I'll be here until August 17th, so I look forward to discussions, and I think next summer we'll be back on a similar schedule. Good. So as a warning, I haven't used one of these things before, so we'll see how this goes. But yeah, I think it should be all right. Good. Yeah. So it's great to be here, and I'll be telling you about work from my group at Gila over the past several years. And as Monica mentioned, I'll really be focusing on just one of the projects in my group, but I'll try to give you an overview of different things going on. Okay. So the work that my group does, and many groups here, and also many groups at Gila and around the world, focuses on this area of quantum information science. Which is represented by a number of tasks such as quantum communication, quantum simulation, computing, and metrology. And each of these share the property that they're trying to leverage some aspect of quantum mechanics to do something that's impossible or much harder to do with classical resources alone. So there are sort of different ways in which aspects of quantum mechanics can give such enhancements. One way is in terms of speedups. And to go through just two examples of this, there's one that I think many people here are probably aware of. So that's one in computing. And here the idea is that if we have a computer made of quantum bits rather than classical bits, it's not as if every single problem that we would compute on this quantum computer is somehow more easily solved, but rather that there are a class of problems that we can do more quickly. And so one good example of that is the problem of factoring, where, for instance, we might be interested in factoring a 2048 bit key or an RSA key. And by RSA here, I mean an RSA key here, I mean the keys that we use for doing public key encryption, say like all over the internet, secures your bank accounts, things like this. So we obviously care about this. And the key point is that actually factoring large numbers, namely numbers this large, is very hard to do. So in a classical computer, we can compare the performance to a quantum computer. I'm showing a classical computer over here. On the right here, I don't want to put any particular hardware because if I did, it'd be somewhat controversial. So instead, I'll put a picture of Peter Shor, who's responsible for the quantum factoring algorithm. And the key point here is that on a classical computer, this will take nearly an exponential amount of time, whereas on a quantum computer, it's polynomial. So in practice, what this means is that the runtime to actually factor a number this large is simply unrealistic on a classical computer, which again underlies the security of modern day encryption. But on a quantum computer, it can take anywhere from 8 hours to a day or a couple of days, depending on sort of the sector of the person that you're speaking to. Okay, so that's an example in quantum computing. There's another example in which speedups arise, and that's in metrology. And so the idea here is we might be interested in measuring some, here we go, quantity of interest, say a magnetic field in our lab. And one way of measuring that would be to probe some transition energy omega naught, which is proportional to this magnetic field. So for instance, a spin flip transition. And here, if I have a chain of unentangled spins and I perform spectroscopy on them, the precision with which I can measure this parameter b, so say delta b here, scales like 1 over the square root of n. This is just due to quantum projection noise, the fact that all of these particles collapse in an uncorrelated stochastic way. By contrast, if I have an entangled system of spins, so say a superposition of all of these spins being up plus all down, then this uncertainty goes like 1 over n. And so what this means is that the amount of time that it takes to actually acquire a given level of precision is shorter for the entangled state case, because if I perform many measurements on copies of this quantum state, I need to do fewer such measurements to get to the same level of precision. Okay, so here too we see an acceleration in a particular task. Okay, so a natural question to ask is sort of how do we get to this level? How do we get to these sorts of enhancements? And this story begins, of course, with gaining control of single quantum objects, not necessarily many of them, but just a couple. And this has a long, successful history in the community with many different platforms, including trapped ions. Wow, this is really a mess. Trapped ions, photons, superconducting qubits, neutral atoms, vacancy centers, and many more. And even in this limit of having just a couple well-controlled quantum objects, there have been really amazing demonstrations, including optical atomic clocks that have the best accuracies in the world for time and frequencies, and furthermore, for fundamental studies of Bell tests. And again, this is just in the limit of having a couple well-controlled quantum mechanical objects. And I want to highlight, of course, that this in and of itself has already resulted in multiple Nobel Prizes. On the left here, I'm showing the work from Serge Haroche and Dave Wineland for measuring and manipulation of individual quantum systems. It's exactly what I said. And in 2022, we also have these recent results using, the recent Nobel Prize of showing, recognizing the violation of Bell inequalities using entangled photons. Okay, so as I sort of alluded to on the previous slides, many of the sort of potentially most impactful applications of leveraging quantum mechanical resources come from not controlling a few particles, but actually controlling many of them. And so the sort of natural path to get there is to build complexity from these well-controlled quantum mechanical objects, sort of assemble from these individual, sort of like this basis set of things that we can control into something more complicated. And this has been exactly the strategy that's been taken in many platforms, including superconducting qubits, trapped ions. So the left here, this is the picture from the Google Sycamore processor, trapped ions. This is from Rainer Blatt's group. And then in neutral atoms, there have been two platforms that have been very successful, including quantum gas microscopes and optical tweezer arrays. And so in this talk, I'll really focus on these two platforms here. And actually, in the beginning of my talk, I'll really zoom in on this idea of optical tweezers. But as I go along here, I'll sort of make allusion to the fact that many of the techniques that we use sort of blend these two technologies together. Okay, so I think many here are familiar with the concept of optical tweezer arrays, but I think not everyone is. So let me just quickly give an overview of what I mean by this. The platform of optical tweezer arrays for control of neutral atoms looks something like this. You have a microscope. That microscope focuses light down, typically through a vacuum chamber window into an ultra-high vacuum environment. This is the environment in which the atoms live, which are trapped by the foci of light made by this microscope objective. Typically, the trap sizes that you can make with a well-made objective are less than a micron big and can localize the position of an atom to tens of nanometers. This gives you a high degree of precision in positioning atoms in space. And the trap depths that you have are on the scale of a millikelvin. So this gives you a sense of energy in spatial scales. Using this same objective, we can collect fluorescence from the atoms and form single atom resolved images, such as this on the right. This is an early picture from my group in 2018. And then when you put this all together, this is a video of atoms, of many runs of our experiment where you see stochastic loading of individual atoms. And the stochasticity in the loading process, I'll come back to later and sort of describe how you can get rid of this. So if I were to sort of zoom in on the sort of specific features of this platform that have made it very successful in recent years, I would really point out the fact that basically what this platform allows you to do is to translate all of these tools that are already established for engineering light fields and translate them into controlling individual atoms. So what are examples of this? So spatial light modulators, these are devices where I can very precisely control the wavefront of an optical field And when I put that light through a lens, it can make a picture like this in terms of the actual light. But because the atoms live at the foci of light, you end up with a distribution of atoms that looks like this. So this gives a high degree of control and versatility in how we can place and manipulate atoms. Furthermore, there are devices like acousto-optic deflectors, which take in an RF signal, which can continuously tune the angle and amplitude and even the number of light fields that emerge from this AOD, this acousto-optic deflector rather, so that we can continuously control the state or positions of atoms in space. Okay, so the applications of this platform have been quite broad. They've been used for a variety of different studies in few to many body physics with all kinds of different interactions and Hamiltonians. Quite recently, there's been a lot of progress in using them for quantum computing, leveraging the fact that you can control individual quantum states quite precisely and even move atoms in real time around to change the actual connectivity of a quantum circuit. A newer direction, which has been ongoing in my group and also Manuel Andres' group at Caltech, has been looking at how this platform might be useful for time and frequency metrology. And then also it has impacted other directions such as quantum interconnects, where the idea here is we'd like to map quantum information stored in an atom onto propagating degrees of freedom like a photon. So this is a picture here from the collaboration at Harvard between Misha Lukin and Vladan Vuletic, where they take atoms trapped in optical tweezers and they're able to get high fidelity interactions between the light field stored in a resonator with these atoms trapped in the tweezers. Okay, so a theme of recent years that sort of was coincident with when I was around with when I was starting my groups, there were a lot of people thinking about this, was expanding this tweezer tool set to more complex particles. A lot of the earlier work had been with alkali atoms, namely atoms with a single electron in their valence shell. But of course, there are other atoms and particles that we might want to trap in tweezers. So these efforts are represented by, for example, trapping molecules in tweezers. This is a picture from Kangquan Ni's group and also John Doyle's group. Dual species experiments where two different alkali species are simultaneously trapped. And the goal here is that you can sort of salvage nice aspects of one atom while simultaneously getting those of another atom. And then finally, trapping alkaline earth atoms in tweezers. These are atoms with 2 electrons in their valence shell. And so this has been ongoing in my group at Jella, Manuel Andres' group at Caltech, and Jeff Thompson's group at Princeton. And I'll try at the beginning of this talk to give you a sense of all the different things going on in this space. So you'll hear these names again in a bit. And I'll highlight as well that there are, of course, here too, a number of different groups building up platforms in this direction. Okay, so at Jilla, my group has been exploring several different directions in this context. So using alkaline earth atom arrays, we've been looking at many body physics, namely itinerant Hubbard physics, using this sort of new technology that we've been working on. We've also looked at quantum metrology, that is the task of using entangled states to enhance the precision of measurements. This is the sort of example that I was referring to earlier. And then finally, also for quantum computing, which I touched on in my seminar at the group retreat last week. Another direction in my group more recently has been looking at how to combine cryogenics with ultra-cold atom systems. There are a couple of different things we're interested in here. So in one project here, we're in this direction, we're attempting to trap optical tweezer arrays in a cryogenic environment with high optical access so that you can, for instance, have control of Rydberg transitions and high fidelity single qubit gates all in one system. There are many reasons you might care about this, but one is to have long vacuum lifetimes. And so we've recently showed having in this environment 3,000 or in excess of 3,000 second lifetimes for a trapped atom array in this cryo system. These features of a cryogenic system might also be useful for getting to very low temperatures in the Fermi-Hubbard model. And we are actually setting up a new project in this direction as well. And for all of these experiments, it's been a collaboration with Cindy Riegel at Jilla. And then furthermore, on this tweezer array project, we've been working with Dan Schlichter at NIST. And they have a lot of expertise in this cryo direction from their trapped ion systems. Okay, so today, I'm really going to focus on this top row here. And let me begin by first giving you a sense of sort of all the things going on with alkaline earth atom arrays. Over the past 5 years, I expect that this will, I won't be able to do this in a single slide as I'm about to do in the future because of all the great things going on here. Okay, so Alkaline earths are different from alkalis, namely in their spectral structure. So they have a variety of different atomic levels, and each of these levels have different lifetimes, which give rise to different transition line widths. And these different line widths enable different kinds of science. So for instance, there's this transition here between the single S0 ground state and this triplet P0 excited state, which is known as the clock transition. And I'll explain later in the talk why it's called that. But this transition is perhaps the reason this atom is most famous, and it's because it enables all of this high precision timekeeping that I alluded to before. So one of the things that we've been looking at, as I mentioned, is combining this transition with all the control that we have with the tweezer system in order to prepare tweezer clocks. Another direction of interest in this community is using the fact that in these 2-electron systems, the nuclear spin can completely decouple from the electronic spin. And this gives rise to a new kind of qubit in these atoms known as a nuclear spin qubit. And so we've been looking at this in my group, and also Jeff Thompson's group has been looking at this. And I'll mention something really exciting they've been doing in just a moment. There is also a Rydberg transition that can be driven, which allows for engineering strong interactions between atoms in these systems. This can be excited from this triplet P0 state to a Rydberg series up here. This was really pioneered in Manuel's group at Caltech, where they showed for the first time the high fidelity Rabi oscillations on this transition, and actually in any neutral atom above 99%. And they've since improved on that, showing that using this transition, you can get to Bell state fidelities as high as 99.8% on this Rydberg qubit. And they've leveraged this for a variety of different directions in high fidelity many-body physics. Importantly, this same transition can actually be combined with this nuclear spin qubit down here. And Jeff Thompson's group has shown how actually this the existence of all these different levels can give rise to very smart protocols for doing more efficient quantum computing using an idea known as erasure conversion. And so I won't define that here, but the basic point is that you can detect errors more easily and therefore encode robust information more efficiently. In addition, there are transitions that can be used for narrow line cooling and also broadband detection of the atoms. All of these features have been used in these various directions that I just discussed. One direction that we've been using it for that's distinct from these is this idea of Hubbard physics, where basically by using this high fidelity ground state cooling, we can prepare individual atoms in their motional ground state in order to initiate Hubbard physics. And this is a picture here where we rearrange an array of atoms and then allow them to tunnel in an underlying lattice potential. And this gives rise to, as I said, itinerant Hubbard physics. And then for this experiment here, we were looking at the idea of boson sampling. Okay, so in this talk today, I'm really going to zoom in on this topic of optical atomic clocks. And in particular, first, how we use these sort of transitions here for doing rapid control and preparation of individual atoms for a clock. And then furthermore, how by adding in this Rydberg transition, we can actually prepare entangled states of an optical atomic clock. Okay, so to tell this story, I really need to begin by, sorry, I just need to drink water. Defining how an optical atomic clock works to sort of motivate why these tweezer systems might be useful for them. And so the basic idea here is that a clock operates like any clock that you're used to. It relies on some regular periodic behavior. The periodic behavior that we're relying on in an atom might be, for instance, the oscillations of the light field that would drive a transition between two states of this atom that's stabilized to this transition energy. Alternatively, and perhaps more intuitively, you can think of this as really just the oscillations of the dipole induced in an atom, which quantum mechanically is just the precession on the Bloch sphere of the coherence of the superposition, which is winding at the energy difference between G and E, the two states that you've superposed. In an optical atomic clock, sort of in more detail, the way this works is you have a laser, which acts as your freewheel on the passage of time, because we can only probe the atoms every so often. And this laser performs spectroscopy on this two-level system, this transition in the atom, and in doing so, figures out the frequency difference between the laser and the atoms, and then feeds back on the laser to make sure that it stays on resonance with this transition here. And so the stability, which corresponds to the relative precision between the frequency of this laser and the frequency of the atomic transition as a function of time that I average for, tau, depends on the frequency of the transition, omega EG. I'm really struggling here with this laser pointer, I'm sorry. the number of atoms and that we can interrogate, and also the coherence time between the atoms in the laser. And so this coherence time depends on, one, just the coherence time of the laser itself. And miraculously, there's been amazing advances in this field. This is a picture from Jun Yi's lab and also the PTB group, where they've shown oscillators, optical oscillators with line widths below 10 millihertz. And then on the atomic side, we also need to make sure that the atoms themselves can remain coherent for long periods of time. And so this means that we need to be able to preserve quantum coherence within this atom for long periods. And furthermore, we need to have many atoms in order to get this n to be as large as possible. And this just corresponds to this quantum projection noise that I was referring to earlier. And altogether, this limit that we expect in the stability is often referred to as the standard quantum limit for optical or for atomic clocks. Okay, so these alkaline earth atoms are so powerful because this transition that I mentioned before, called the clock transition, is long-lived, and it lives on an optical transition. That is, it's hundreds of terahertz in energy. So in terms of clocks, that means this omega EG you've made to be a very, very large number. And this can be seen, the sort of advantages of this can be seen in the progress, in terms of the progress of the field. So this dashed red line here corresponds to before clocks. I guess I can even call that like BC and like AD, or maybe not AD, but BC at least this way. So if you have microwave clocks before the advent of optical clocks, the frequency of this transition was 10 gigahertz. But then on the right, once optical clocks came around, we have hundreds of terahertz oscillators. And as a result, the precision and accuracy of these systems has rapidly accelerated with time. And so nowadays, these systems can do amazing things. So a trapped ion clock at NIST has reported accuracies below 10 to the minus 18. So for reference, this means the frequency of this transition is known to a millihertz out of a petahertz. Then on the optical lattice clock side, where many, many atoms are trapped in a standing wave of light, here, because you have many atoms compared to the trapped ion case, where you have one to a few, the quantum projection noise is much, much lower. And so very quickly, these systems can acquire precision. This is a plot here showing you a very, quite an amazing result, where in the Yi group, they were able to measure the gravitational redshift between two regions of space in an optical lattice clock on precisions below 10 to the minus 20, and on length scales below a millimeter. Okay, and so these platforms have been proposed for a variety of different directions in the community, including fundamental physics like time variation and fundamental constants, geodesy, and navigation. And the sort of proposals coming out are sort of increasing by the day. So one of the things that my group was interested in was whether there might be room between these two platforms for something which exploits the control that you have in these trapped ion systems, and also the scale that you have in the lattice clock systems. And so in 2019 and 2020, my group began looking at this. And so I don't have time to go through all the details of how we sort of came to where we are now, but I'll just highlight that in 2020, we had this, we came up with this protocol where we could load 160 atoms in tweezer arrays that were so-called magic for the optical clock transition. That means that they don't perturb the clock transition frequency when the atoms are trapped in that wavelength of light. And it's important to be able to do that in order to have reliable spectroscopy. And it turns out this was somewhat difficult because basically every other task that you might want to do in these experiments works less well at 813 nanometers. So we came up with this protocol of using two different wavelengths of light where we could load between these different tweezer arrays to perform different tasks in the experiment. And this allowed us to get to this larger atom number of 160 atoms. And what we were able to find at that time was that the ensemble coherence, that is how long the atoms remained in phase with one another in this ensemble, was nearly 20 seconds long. This was the longest, at that period of time, this was the longest coherence time that anyone had observed. So this was really showing the kinds of how the tools that we have in this system can really illuminate fundamental features of optical atomic clocks. And then furthermore, by using a technique known as correlation spectroscopy, we could actually see that our single particle coherence, that is how long the dipole of a single atom its phase was well defined, persisted for about 48 seconds. And this was consistent with what we expected based on basically all the other characterization we had done in this system, corresponding to a quality factor of 6.5 times 10 to the 16. So this is basically saying something like, if you had an oscillator that you began at the Big Bang and it was ticking on the scale of a second, it would still be ticking today. That's the order of magnitude that we're talking about as far as what this quality factor corresponds to. And so putting this all together, having the large atom number and these long coherence times, we were able to see stabilities of 5.2 times 10 to the minus 17 per root tau, which was on par with the state of the art at that time. So altogether, this told us that this platform could be competitive as an optical atomic clock. And I want to highlight that, oh, well, something got messed up with my slides here, that there's still some ongoing studies here that need to happen, for instance, doing a full systematic accuracy budget for these systems. Okay, so one of the things that we were interested in this setup was not just looking at how this platform might be used for time and frequency metrology, but actually if you could use it for quantum metrology. That is this idea of combining, say, a well-controlled optical atomic clock with entangled states. And importantly, these tweezer systems at around beginning in around 2015 started demonstrating having high fidelity entanglement in larger and larger systems. So this really motivates the idea of sort of combining these two ideas to prepare long-lived entangled optical clocks. And so I want to highlight that this direction in general in the community of improving precision using entanglement is actually somewhat practical. It's already had a number of impacts more broadly and beyond optical atomic clocks. So for instance, modern day LIGO uses squeezed light in order to get to its to the performance it has today. So for instance, the green here corresponds to the more recent version of LIGO, which uses squeezed light, and the black is before they injected squeezed light into their interferometer. There was this really cool result from a collaboration at between Gilla and Yale showing improved bounds on axion detection using squeezed microwave fields. And there's been ongoing group work in optical atomic clocks using cavity QED to prepare squeezed clocks. And this was first demonstrated in Vladan Vuletich's group at MIT. And then more recently, there have been other exciting results at Gilla in a collaboration between James Thompson and Junyi. Okay, so sort of focusing in now on this idea of an entangled clock, it's important to sort of understand what different kinds of quantum states we could produce that might improve the performance of the clock. And this can be well understood in terms of this stability expression that I showed you earlier. So one kind of state that we can create that's pretty well known is known as a squeeze state. And basically what happens here is that under interactions or some operation that I perform on the system, the noise distribution of a spin ensemble, which looks circular like this, is sheared into something that looks sort of sheared like this. And along a particular axis, the variance in that noise distribution is reduced compared to the original state. And so we can use this for enhanced sensing. And basically what's happening here is that you're effectively gaining the precision of an ensemble that was effectively larger than the one you began with. You're sort of adding correlations to the system that allows you to reduce the quantum projection noise of the ensemble size that you have, as if you had a larger number of particles. Another kind of state that you can produce is a GHZ state. And here, when you prepare a superposition of all atoms ground plus all atoms excited, the frequency of this superposition oscillates at n times the transition frequency, which is n times faster than a single particle's transition frequency, a single particle superposition would process. And so effectively what you're doing is increasing the frequency of the oscillator that you're probing, and in doing so, enhancing the stability. Finally, there are other kinds of entangled states that you can produce, which use more sophisticated quantum circuits. This is a picture from a work from Peter Zoller's group, and then also from Rainer Blatt and Innsbruck, where you can basically encode very specific states of interest, which are robust to the kinds of noise that you might have in your system, and actually decode the signal as well. And this is a very versatile approach, which allows you to sort of tune all of these things, plus increase the dynamic range of your sensor. Okay, so typically the way the enhancement from these different kinds of states is parameterized is in terms of this parameter C here, which is known as the Wineland squeezing parameter. And basically when this thing here is less than 1, you have something that has an overall stability which is improved relative to the quantum, the standard quantum limit. So sort of the key point here. So all this is sort of thinking about how to make this parameter less than 1. And so in this first part of my talk, or not first part of my talk, in this first example that I'll tell you, I'll describe how we use this platform that I've been describing for preparing squeeze states. Okay, so over the past several years, we've sort of built up this system that I was introducing earlier to have a lot more capabilities. And so we have this, the structure of the sort of simplified structure of the atom that I want you to think about here is we have this clock transition, which we can control with this control field omega c. But then we can also excite the triplet P0 excited state of this clock transition up to the Rydberg state up here with another driving field omega r. If we just drive coherent Rabi oscillations on this clock transition, we've spent a lot of time trying to make these as high fidelity as possible because you need to make sure that the noise from your oscillator is not affecting the fundamental noise that you might expect from an entangled system. If we add in this Rydberg transition here and just focus on the energy of this excited state, what happens here is that this Rydberg drive admixes a small amount of this Rydberg state into this excited triplet P0 state here. And so what this means is that these Rydberg states, which are strongly interacting, get coupled into the excited clock state E here. And so if we perform spectroscopy on the system, what we find is that there's an interaction potential, which has this soft core behavior. And this strategy of so-called Rydberg dressing was actually first demonstrated in a high fidelity way, sort of upstairs over there in Emmanuel Bloch's group and by Johannes Zeyer. And so the key point here is that we can engineer interactions of a fairly high scale up to 100 kilohertz and with this well-defined spatial profile given by where the atoms sit on the lattice. Okay, when we put this all together, both the interactions and the control on this clock transition, we can engineer so-called Ising models where there's a sigma z, a poly-z interaction between different atoms with an interaction range given by basically that soft core potential that I showed you, plus some longitudinal magnetic fields. And also we can add a transverse field by just putting on this clock transition here if we want. Okay, so that's sort of, did this just turn off? Sounded weird, no? Okay. Okay, so that was sort of a high-level description of what we can do. I just want to highlight that under the hood, to actually get to this level of control, we developed this hybrid tweezer lattice system where there is an array of optical tweezers, which is well registered with the sites of an optical lattice. And so the sort of basic technique is that we have this bow tie lattice that we built into the system early on. If we sort of put atoms inside of this lattice in random locations and then take take many images, we can see something like this, which just shows you all the different lattice sites on which we can load and image individual atoms at high fidelity. So this is about 2,500 lattice sites in this system. And so in this clock direction, it was very important to do this because it allowed us to have scalable detection over many lattice sites and also high fidelity control of the clock transition. Using our previous strategies, we actually would just not be able to do this kind of physics without this kind of technique. Furthermore, I'll just highlight that, and sorry, actually, let me just add, having the tweezers here allows us to still retain all of the single particle control that you have in these systems. So by having the tweezers overlap with the lattices, we can move the atoms around. And I'll show you an example of that in just a moment. Let me add as well that because we have a lattice underlying the system, physics like Hubbard physics can be accessed in the system as well, but in a new way. So how does an experimental sequence in our group look using this sort of basic architecture? So we load a tweezer array of atoms stochastically. So you'll see a random image, a random distribution of the atoms in the lattice. We then use the tweezers to rearrange the positions of the atoms. So this is rearranging the atoms into the CU logo. And then after we've done that, we can actually rearrange them into any sort of configuration that we want. So this is an array of doublets on nearest neighbor sites. This is a rearrangement of atoms on every other site of this lattice potential. This is strontium-88 pointing at a strontium-88 atom. And this is just sort of rearranging a lot of atoms. And we can do this basically at the level of our imaging fidelity of 99.5%. And these are on spatial scales as small as 575 nanometers. And so in doing this, we have control of the density entropy in the system, namely the locations of the atoms. But we also really care about how hot the atoms are at individual sites of the system. And here we use the high fidelity cooling that's possible in this narrow line transition in alkaline earth atoms to do something known as resolved sideband cooling. And the basic point here is that we can cool the atoms to greater than 98% three-dimensional ground state fraction in each of the harmonic oscillators that the atoms live in inside of this lattice. Okay, so then the motion is also controlled. We can then let the atoms go in the system if we want and let them actually tunnel. And let me just quickly highlight before I move on with this clock story that sort of the way this kind of experiment looks is if we rearrange the atoms, say in this distribution here, and then do single shot resolved images, the atoms in this lattice as they tunnel is very similar to photons traversing a beam splitter network. So we use this, for instance, to look at the idea of boson sampling, but in this case, doing it with atoms. And we were able to see in this work that actually the purity with which we can prepare these atoms, the single particle purity, is about 99.5%. So it's really, we were using the indistinguishability of the atoms to back out how well we were preparing them. And this, I think there are many different directions that we can go with this. For instance, if we look at the dynamics of non-interacting isotopes versus interacting isotopes of strontium, we can see very different dynamics associated with the transport of the atoms in the lattice. Okay, so coming back to this clock story, I just want to highlight that. The key thing that we wanted to do here, as I mentioned, was prepare squeeze states on this clock transition. And to do that, we used this proposal from Thomas Pohl and Matt Jones from 2014. And the basic idea is as follows. So if I have this Ising interaction potential that I showed you earlier, it's actually not obvious that you can get good squeezing with this because it's not an all-to-all model. And let me sort of walk you through why that is. So if I have this distribution here, and I make sure that the atoms are spaced by a distance which is much less than this characteristic distance RB, which sets when these interactions fall off, then effectively what I have is a so-called one-axis twisting model where there's an all-to-all symmetric ZZ coupling between all the individual spins. And this gives rise to exactly these shearing dynamics that I was mentioning earlier. The idea here is that if there's a rotation imparted to the spin distribution, which is dependent on the projection of SZ. And so if I start with this coherent state, I end up with this precession of the noise distribution, which after a rotation, I can realign with the y-axis of my Bloch sphere, which means I can then measure displacements more precisely along this direction. And so we can do exactly this. So we prepare 2 copies of a many-body state. You'll see in a moment why we do 2 copies. But the key thing here is that we have these 2 ensembles which are strongly interacting within a copy, but there are no interactions between the copies. We apply pi/2 pulse and then apply this Rydberg dressing protocol. We reorient the Bloch sphere and then inject that squeeze state into a Ramsey sequence. And then what we look at is the difference in the average spin projection as Z between the top copy A and the bottom copy B. And the key reason we do this is it allows us to back out the fundamental quantum projection noise of these 2 ensembles in a way that subtracts off the laser noise that we have in this system. So basically, we can't fully get rid of all the laser noise in the system, even though we're working with the state-of-the-art system at Gilla. And so in doing this, we can actually look at the fundamental quantum projection noise. And so when we do this, we see something as follows. So this is a plot here of the variance reduction, so that just of the noise distribution versus the orientation of that noise distribution. So that's just basically rotating this ellipse here. And you can see that for certain angles, the noise in our system falls below the quantum projection noise. That is the noise of an uncorrelated coherent state. The solid gray line here is our independent calibration of the standard quantum limit, and the squares are our measurements of the standard quantum limit when we just don't apply the Rydberg dressing. You can see also that At other angles, the noise is enhanced. That's when we've aligned this longer axis of the ellipse with the y direction on the Bloch sphere. One thing that's nice about this system is that we can actually study the microscopic correlations that are responsible for this squeezing. So for instance, where we have variance reduction, what's occurring, what we observe is that there are negative correlations between the atoms. And these negative correlations are exactly what you'd expect, because when the atoms collapse, if they're anti-correlated, and for example, I'm measuring SZ equals 0, if they're anti-correlated, then they're more often going to be sort of collapsing like this versus this and this. And so that means that the overall noise in that measurement of SZ is actually reduced. By contrast, if I have excess noise, or sorry, if I have excess variance, that corresponds to where the atoms are more likely to collapse in a correlated way. So this would be like having excess up, up, and down, down populations. There's more fluctuations in SZ as a result of that. To understand the amount of metrological gain that we expect from the system, we care not just about the variance reduction, but also about the contrast of the resulting interferometer that we would get if we inject this squeeze state into the system. This is basically saying that if we're looking at precession on a Bloch sphere and we want to measure an angle, we care about the size of the Bloch vector. If that Bloch vector is shrunk to 0, we're not going to be able to measure an angle. And so what we find is that the Wineland squeezing, which is again a measure of this, falls to about 4 dB at a pretty short interaction time of about 2 microseconds. So this is really showing and certifying that in this system, we would expect to have metrological gain. I want to highlight that at the time of this work, there were several experiments that were performed, which all showed in different ways squeeze states using short-range interactions. There was a beautiful experiment from Antoine Brouweis's group, another by Monica Schleier-Smith's group, and then finally another in the Innsbruck group. And again, these all had different nice features that sort of illuminated the interesting many-body physics occurring in these systems. One of the things that was unique about our work is that we actually injected this into a clock to do a frequency comparison to actually verify that we have a metrological gain in an operating clock. And this was actually the first time that this has been done in a clock. And so the idea here is that in purple is the stability as a function of averaging time when we inject squeezing into the system, whereas in gray is that same measurement when we don't. And if you actually look at the noise distributions from these two cases, you can very clearly see the narrowing in the noise distribution for the squeeze state. And overall, we were able to see that in the clock sequence, we had about 3.5 dB below the standard quantum limit enhancement in performance. We could also go to a larger number of atoms, which allows us to improve the stability just by having more particles, but we saw a slight degradation in the overall squeezing to about 2 dB below the standard quantum limit. Okay, so that was a story about preparing squeeze states. In my last bit here, which I think I have 15 minutes, right? Right, okay, cool. I'm gonna tell you a different story, which is about, rather than preparing squeeze states, preparing GHZ states. And this begins with something a bit interesting. So let me sort of tell you this story. So in 1997, actually in 1994, people were very excited about using entangled states for metrology. There was this very famous paper from Dave Wineland that actually sort of first put forth this idea of the Wineland squeezing parameter, although he of course didn't call it that. And then in 1997, Ignacio wrote this paper that basically was like, sorry, none of this is going to work. You should just go home. And so the basic idea is it was much more polite than that. But the basic idea is as follows. So if I have a GHZ state, I told you that it improves your sensitivity by root n because you've increased the frequency of your oscillator n-fold. Of course, the problem is that if I have any decoherence process, the rate of that decoherence process is also going to accelerate n-fold. And so what that means is that if I consider what is the optimal dark time for performing a clock sequence, the optimal dark time for the GHZ state is going to be n times shorter and exactly offset the gains that I would have had in using an entangled state. And basically that's what's shown in this plot here, that you get to the same stability for a coherent state, so n uncorrelated particles, as n maximally entangled particles in a so-called GHZ state. Okay, so that sounds somewhat sad, but let me point out something about this paper, which is that what it focuses on is noise from single particle processes such as decay, But if I have correlated local oscillator noise, then this story is slightly different. And let me sort of walk through what I mean by that. So this is a picture of a Ramsey sequence, data actually from my lab. And there are different sort of theory models on here that show you different forms of dephasing that occur. So this light gray swath here corresponds to decay processes that give rise to loss of the atoms and also decay of the atoms from the excited clock state. This dark gray here corresponds to dephasing because of frequency distribution in the frequency of the clock transition, plus all of these decay processes that I just mentioned. And then this solid gray line here corresponds to our model of the atom laser dephasing. That is the dephasing of the atomic oscillator relative to the frequency of the optical oscillator. And so the effect of this on this transition can be better understood if we just sort of zoom in on these different parts of the plot. So on 0 to 3 seconds, if we look at this Ramsey fringe, we see a well-defined sinusoidal oscillation as we'd expect of a Ramsey fringe, okay? So at that time, we have both atom laser coherence, that is coherence between the atoms and the laser, but also the atoms are coherent with one another, right? If they weren't, then we wouldn't actually see anything here because they would respond differently to the laser. At 20 seconds, the fringe is completely scrambled, which means we're seeing phase slips between the atoms and the laser by more than pi on the time scale of the Ramsey fringe. But there are large fluctuations in the overall SZ that we measure. And what that means is that all of the atoms are responding to the laser in the same way, right? If I have all of these atoms that are processing and pointing in the same direction, if the phase of the final pi/2 pulse in a Ramsey sequence is random with respect to them, some of the time they're all going to go up, and other times they're all going to go down, and some of the time they're going to be at 0. Whereas if they were all dephased with one another, every single time I'd measure them, I would just get 0 polarization of the spin. Okay, so there's no atom laser coherence there, but there is atom-atom coherence there. And then at late times, we see exactly this case that I just described of both no atom laser coherence and no atom-atom coherence. So the question is, if there's a well-defined but unknown atom laser phase, can we still actually do improved metrology with this system and with GHZ states? So to sort of motivate how that might be possible, let me first explain how you would use GHZ states in a metrology sequence. So if I prepare a GHZ state, I have the state here of all G plus all E. This guy winds, as I said, at n times the detuning between the atoms and the laser, and the overall phase that it picks up is just the dark time of my Ramsey sequence times the detuning between the two. And then in these sequences, what one typically does is they measure the parity. This is just the overall like x to the sigma x to the n correlator. And this thing varies like cosine of n times phi, where again, this phi here is just something which is linearly sensitive to the frequency of the laser, the detuning between the atoms and the laser. So let's now consider two cases. So if I have an n equals 1 GHZ state, which just means a single particle, this quantity, the parity, goes from -1 to 1 on the range of the atom laser phase from -pi/2 to pi/2. But the n equals 4 GHZ state, it actually oscillates 4 times on this interval. And so let's imagine if we're trying to stabilize a laser using using these fringes. So if the laser, so this sort of highlights this point here that the slope here is steeper, which corresponds to increasing this omega EG. If the frequency of the laser is at this, gives rise to an atom laser phase given by this red line here, then I'm in a regime where I can accurately invert the signal and steer the laser back to the origin for both the n equals 1 state and the n equals 4 GHZ state, because I'm in an interval here, which sort of makes sense. But if my laser fluctuates over here, then I'm in a regime where while I can invert the signal for the n equals 1 case, I actually don't know what to do with the laser for the n equals 4 case, right? Because there are multiple places where this line intersects and gives rise to the same value of the parity. So this gives rise to a problem when I'm trying to actually figure out how I should steer the laser. And so this basically suggests that this interval is actually n times smaller for the GHZ state case of n particles. And as a result, it might seem that Ignacio's result sort of dooms this prospect, even when you have good coherence between the atoms and between different GHZ states, but not between the atoms in the laser. But there's actually a solution here. Let me skip this part. And the solution here comes from the idea of using multi-ensemble metrology. And this is a slide that was actually designed by, or put together by Nelson Darkwah-Apong, who I think is familiar to many of you here. He's a postdoc in my group and is now starting a new group at Caltech. If you're looking for postdocs, I highly recommend joining his group. So here's sort of how you can solve this problem. So imagine I have a distribution in the laser phase that looks like this Gaussian here, which is like a pretty good model for how things might look in a clock. So any given run of the experiment, the laser phase might be at some value. Let's say it's at phi naught here. And if I have that n equals 4 GHZ state, as I showed you, that line might intersect at a particular value of the parity, which is compatible with multiple different phases of the laser, as I said. And so what I could do is figure out the probability to observe a particular parity given the value of the laser, just based on an analytic model, that cosine n phi that I showed you, and then multiply it by the laser phase distribution, and then just pick the value that's most likely given the product of those two probabilities. Sort of one way that I could do this. And what I would guess in that case is this probability right here, which, as you can see, is actually wrong, right? That's not the right phase. However, if I have multiple different GHZ states, each of which is winding phase at a different frequency, I can keep track of all of these different phases in parallel in a single run, and multiply all the resulting probability distributions from those different sized GHZ states. And when I multiply them all together, I get a much, much better estimation of what the phase of the laser is. And so the basic idea is that by having multiple different frequency oscillators, I can unwrap the phase reliably. And the prerequisite for doing this is just having all these GHZ states in parallel. And so this notion of so-called cascaded GHZ states was first proposed in 2014 in a paper by Misha Lukin, and actually Juni is also on this paper. And it sort of builds off ideas in the community, both from entangled and non-entangled systems in photonic interferometers and also in clocks. And in recent work from my group, we've been exploring this idea, and in particular, rearranging atoms on a lattice in such a way that we can, in parallel, make many different sized GHZ states with which we can do more reliable high dynamic range phase estimation. And just to highlight this point, these atoms in different clusters here, they correspond to, say, 3 copies of an n equals 2 GHZ state, which winds a single particle phase theta twice as fast. I have 2 copies here of an n equals 4 state that winds at 4 theta, and so on. You get the idea. And so it suffices to figure out, is there a way to actually prepare these states both at high fidelity and also in parallel? That's sort of the main problem or challenge. And so in our group over the past year, we developed, in collaboration with Sven Yandura and Guido Papillo, a family of multi-qubit gates. These are gates which realize this unitary U here, which looks like e to the I pi over 2 n squared. The key point here is that if I apply this unitary to a product state of all particles pointing along the x direction, it prepares a GHZ state. And so it turns out that just by optimizing the phase of the Rydberg laser that we use to excite the atoms, we can realize this unitary. This is based on advances from, as I mentioned, Sven and Guido. And so what this does, this unitary here, is it effectively implements this circuit here. And one crucial thing about this is it's actually robust to particle number fluctuation. So for instance, if I lose one of these particles, say here, or I improperly rearrange the atoms, because this circuit is symmetrized over all the atoms, I still get the right unitary. As long as the particle isn't lost in the middle of the circuit, then I still have the right things. This is very robust to preparation infidelity in our system. And so at a 2-particle level, we can prepare high fidelity Bell states on the clock transition using this technique. To my knowledge, these are the highest raw Bell state fidelities that have been reported for neutral atoms. And we exclusively care about raw Bell state fidelities because all forms of error in the system dictate the resulting contrast of the interferometer, that we would use in a clock sequence. We can also scale this to larger numbers of particles, where we go up to, in this case, up to 9 particles, and see that we still have pretty high fidelity contrast in the system. The overall fidelity is decaying as you'd expect as we go to larger numbers of particles. And in blue is the overall fidelity, and in gray is actually the contrast, the parity contrast, which actually sets the precision that we have using these GHZ states. We can take just a single GHZ state and do an atom laser comparison. And what we see is that indeed there is an improvement in using an entangled state that's shown in purple relative to a coherent state shown in black. This is done with 9 copies of a 4-particle GHZ state. And so we get a relative improvement between the two, and we're just barely below the quantum projection noise limit for the entangled state. But we actually have to operate at this rather modest dark time of 3 milliseconds. And this is exactly because of these problems that I was mentioning, that we're more sensitive to atom laser fluctuations. And so the key is then we need to not just operate with one GHZ state, but many different sized GHZ states, as I said. And I mentioned this point just 2 slides ago about how this is robust to particle number fluctuations. And it's actually even better than that. What it really is that not only is it robust to particle number fluctuations, but it actually implements the correct unitary for all particle sizes less than some maximum number. So for instance, if we optimize the phase of our Rydberg laser to prepare a GHZ state for 10 particles that are all within a blockade radius of one another, then it also does the same for all cluster sizes less than that number. And so that means that in parallel, we can prepare a GHZ state, we can in parallel prepare GHZ states of different sizes using this approach. And so that's exactly what we did. So we rearrange atoms into a configuration that looks like this. You can see here that up top, this is 2 copies of 8 atoms that'll be turned into an n equals 8 GHZ state, and the same for n equals 4, 1, and 2. Effectively, the unitary that we're producing when we do this looks like this. When we perform parity oscillations on the system, we see exactly what we'd expect, which is that we have multiple different frequency oscillators given by the different GHZ state sizes. We can then put that all together to do phase estimation with the system. And what I mean by that is we inject a particular phase for the final clock pi/2 pulse in our Ramsey sequence and compare it to our guess of what the phase was based on our measurements of the sample. And so this is a measurement of such a process, and you can see that ideally you'd want this to sort of sit on y equals x for the whole scan of the plot. But as you approach the edge of where you can invert the signal, it gets worse and worse. For contrast, this is the dynamic range, that is the range over which you can invert the signal for an n equals 8 GHZ state. So this is really showing you that over this whole dynamic range, we have improved performance. I'll add as well that this is a sort of more complicated plot, but usually the way this is looked at is in terms of something known as the mean squared error, which just shows you the range over which you have a high precision measurement of the phase. And maybe just focusing on the solid red line here, you can see that that range is much broader compared to what's in green, which is the n equals 8 GHZ state. But you can also see that the error that we get to in our system is actually above what you have for a coherent state. And the reason that is because of the errors in our preparation fidelity for the GHZ state. So we don't get below SQL here, but we do demonstrate a large dynamic range as a result of this cascaded preparation. Okay, I think I'm low on time here, so I'm going to skip that last slide, and if there are questions, I can come back to it. So maybe just as an outlook here, we've looked at these different kinds of entangled states for metrology. I think there are a lot of different directions that one can still go in with this. So for instance, a whole part of the field has been looking at these ideas of atom atom comparisons beyond the coherence time with the laser. This is actually what we were doing when we were looking at these coherence times of 20 seconds and longer. And it's an open question whether in these kinds of systems you can use entangled states to actually gain improvements in performance. There's sort of some subtleties here that are pretty interesting. There are ideas for using these sort of more complicated circuits to optimize the entanglement and therefore the sensitivity of your sensor. This is really began with work from Peter Zoller's group. Understanding the many-body physics in these systems, such as these squeezing experiments that we've done, is actually an outstanding challenge for us, and we think we've made some headway on this in hopes that we might actually improve the squeezing further. And then finally, there are some very interesting ideas using mid-circuit operations, that is, performing measurements on a subset of your sample, such as you would do in a quantum computer, without perturbing the other qubits. And it turns out that that kind of technique can actually be very useful for Heisenberg limited metrology. Okay, so with that, let me conclude. I want to highlight the people who were leading this work. So that's Alec Tsao at the top here, sitting on top of a mound of rocks. Nelson Darkwa Pong, Aaron Young, Will Eckner, and Theo Lukin-Yellen. And then also postdoc alumni, Matthew Norcha and Nathan Shine. I also want to highlight our collaborators in June's group. And finally, also the cryo collaborators that I mentioned in the beginning. Thank you.
Okay, thank you very much for this great talk. So now questions. No. Okay. Yes, please.
Yeah, for the squeeze state, what is the squeezing level you can achieve, and what is limiting the squeezing level?
Yeah, that's a good question. So, so we get to about 4 dB of Wineland squeezing in this system. What we expect, so if you look up here, the solid purple line here is what we would expect for just doing exact diagonalization on the system. And you can see that our data is actually worse than this. And the reason it's worse is due in part due to a collective loss process that occurs in the presence of the Rydberg interactions. And actually recent work that I decided not to talk about, inspired by actually experiments here, has allowed us to reduce this noise substantially. So we expect that we can get to higher degrees of squeezing now, revisiting this work. Yeah.
Okay, great.
Yeah.
Thanks, great talk. I was wondering if it's also possible to engineer something like 2-axis squeezing there systems, and would this help, like in terms of the metrological gain?
Yeah, that's a good question. So it is more difficult to. Oh, what did I do?
Time's up.
Huh? All right. Well, talk's over. No, it's still on. Oh no. Quell. It says, what does quell mean in German?
No signal.
Oh, maybe
No source.
no source.
Seems like
Okay, I'll start answering that question while this maybe resolves itself. Oops. Okay. So the interactions that we get just by exciting the same parity Rydberg states don't naturally give us a 2-axis twisting Hamiltonian. Cool. But people have been looking at trying to do this in other kinds of systems, such as cavity QAD systems, and also polar molecules, actually. And there were 2 papers, one from James Thompson's group and another from Juni's group, recently doing this. And the advantage, as I think you're alluding to, of using a 2-axis twisting model is that actually the scaling of the squeezing that you can get versus particle number is improved relative to a 1-axis twisting model. That's something that I would say is harder to do naturally in the system, but you can also prepare GHZ states that have Heisenberg limited sensitivity.
Okay, thanks.
Yep. Do you have a question?
Yeah, I like this idea of using GHZ states for metrology and kind of preparing GHZ states of different sizes to estimate the phase. I was wondering how this compares with the standard behavior of 1/(n) as a function of particle number. I guess you wouldn't get the naive kind of 1/(n) scaling anymore because you need more resources.
Yeah, no, that's exactly right. So what you get is what they showed in Misha's paper as log n/n. It's actually a little bit more subtle than that. So we did some modeling on it. This is like the slide that I skipped. And so the point is that basically, sort of focusing on this plot here. So this is the relative variance versus the total atom number. where total atom number here doesn't mean the total size of the GHZ state. It corresponds to the total number of atoms to which we have access. And we assume that we can distribute them how we please, right? We could just make like mk copies of the nk size GHZ state, and I could have k different sizes of this GHZ states. That makes sense? So you can sort of optimize over that. And in black is what we sort of think is the best that you could do when you include the fact that you can't beat the errors from Rydberg decay when doing these gates. And then the ideal is shown in lighter gray, which is sort of nearly matching this limit that you'd expect from that paper. So you can't quite hit exactly Heisenberg, but you get very close because it's log n over n.
But sorry, so here for n total, you have different sizes of GHZ states.
Yeah, so like an example of a particular partitioning would be, suppose n tot equals 100. This would be like 10 copies of an n equals 10 GHZ state.
Okay, so it's all the same.
No, it doesn't have to be. I'm just giving you an example. It could also be like, one copy of an n equals 10 GHZ state and 90 single particles.
Yeah. Okay. Did you have a question? Okay.
So you were showing these multi-qubit gates, and so what does actually multi mean here? So how many qubits do you feel comfortable with to entangle?
So you were asking a slightly different question, or going to ask a different question. So we went up to n equals 10 here. I showed only 9 in data, but in the lab we went up to n equals 10. And sort of you're asking actually theoretically, like how large do I think we could go?
Well, also practically. I mean, what kind of gates can you even implement, and can you make a toric code out of this, for example? So.
Yeah. So the main considerations here that you have to balance are, on the one hand, this gate sequence relies on being in the blockade limit for all the particles, though we're actually going to now explore whether we might be able to relax that a little bit and see whether it can still work. So that's sort of a caveat to everything I'm about to say. But if you're sandwiched between everything needs to be within a blockade, but you also need to make sure they're not so close together that you're in the so-called like spaghetti limit of the Rydberg interactions, you're sort of limited to how big a system you can make. And that's going to scale roughly with both the sort of technical limitations and how closely you can pack the atoms, and also how large a principal quantum number you can go to. And that's sort of like an experimental investigation, so it's hard to say.
Thanks.
Yes.
So can you put back the figure in which you draw exactly the previous questions, in which you draw exactly that one here? So what will happen in the asymptotic limit? So you take now into account the Rydberg decay, and you would take n going to infinite. Would it saturate to some constant, or would continue go down?
It's going down. Yeah, because the Rydberg fidelity does not limit the Ramsey coherence time, right? It just limits the fidelity with which we can prepare a given size GHZ state.
Right, but if at some point you have a big GHZ state and one of the atoms goes wrong, I mean, just gets a phase.
But we're not preparing, when we do this, we're not preparing different, you're not going to arbitrarily large n here, right? You're changing the partitioning here.
Right. No, I'm saying if you increase the number, now if you have more and more atoms, you have 1 million atoms, then if you want to increase, you will have to create bigger and bigger GHZ states, otherwise it will saturate. But if you prepare bigger and bigger GHZ states, now the Rydberg at some point will take over, and the errors will be due to the Rydberg states, because just one error in the GHZ state will kill completely that GHZ state.
I need to think about that. That's a good question.
Okay.
Yeah, that's a good question.
All right. So let's thank Adam again for this.
Oh, wait, maybe we have a couple of questions from Zoom.
Sorry.
Do we have them? Nice. That's great.
Okay, so let's thank Adam again for this great talk.
Yeah, just a quick announcement. First of all, if you didn't do so yet, we're probably going on a record today. So just fill the sheets of the participants of the colloquium. We need them for the documents. And another thing, this is the last colloquium for the season. And the next time we will be super happy to see you is